Alright, so this is probably going to be the shortest study guide ever. But yeah, I think we're going to be breaking another record. So, we're going to be talking about Venn diagrams, sets, and types of probabilities and events. So, despite it sounding like a lot, it's literally just this. And yeah, welcome back, guys, to the study guides, and welcome to term 2. You're reviewing for the first assessment for mathematics. So, this is a very short topic, it only covers 3 sessions. So, let's get immediately started. So first, what I have over here is the first topic is the Venn diagram. So let's talk about. I'm going to show you how to read sets. So first and foremost, okay, let's use a different colored marker so you can see, and I'll lower the opacity. So first and foremost, the question is to find the probability of picking let's say an event that's within this set. So there's 10 entries at A, and then we have 2 entries in the middle. This is called this intersection is called A union B. A intersection B, because this is where the A and B meet, and this is called B. So we call this 10 part of set A. We call this 2 part of sets A and B, while this 12 is just part of B. So let's get started. So first one, what is the probability of choosing an item that's within just set A? So first and foremost, obviously you can shade this region over here, because as you could see, it's part of A, obviously. However, what you can also do is also shade here, the number 2 here. Why? Because it's part of sets A and B. And we're looking for items that have, that have part of either sets. So this is what you call set A. So if you're asked set A, you shade it like this. So that's going to be 12, because 10 plus 2, over, so 10 plus 2 is 12, plus 12 is 24. So that's equal to 1/2. Very good. Now similarly, you can also apply the same logic here. Okay, let's erase this one. So B. So like I said, letter B. Let's use a color, blue. Let's use blue. So like I said, obviously this is B. This is B, because as it's clearly highlighted here, B. But you can also highlight the 2 in the middle, because it's part of both sets A and B. And as you can see, I said B, so we're going to count it towards. So 12 plus 2, that's 14. So we're going to go over here. It's going to be 14 over 24, or 1 simplified, that's going to be equal to 7 over 12. Next. Alright. Part 3, A and B. So A and B is going to be what's the part that contains both sets A and B. And as I've previously mentioned, it's just going to be this 2. Oh, opacity. 2. This 2 over here. So therefore, it's 2 out of 24. 2 out of 24, or that's equal to 1 over 12. Alright, next. Number 4, not B. So we're only gonna shade the one. So basically, if it contains the letter B, we're not gonna shade it. So obviously not this one, and also not the intersection, because it's part of sets A and B. So therefore, what we're only gonna shade is this region over here at A, which is just 10. So that's gonna be 10 over 24, or that's equal to 5 over 12. So very nice. And then lastly, A or B. So let's ask ourselves this question. We got this one, A or B, so it contains A and B, so it contains A or B, and then this one, B, which contains A or B. So as you could see, everything in the diagram is shaded, which means it's 24 over 24. Whoops. 24 over 24, or just equal to 1. So let's check the answer key. Okay, let's not show the other answers though. And okay, 6 over 13, 7 over 13, half. Okay, sorry, this is a bit erroneous, but this is all correct. Sorry about that's not the answer key. Sorry, but this is all correct. I've proven it. Yeah. So this is the correct answers. Sorry about that. I think we got a mix match. Okay. Now I'm gonna show you how to read the diagrams. So first and foremost, letter A. How many in this diagram? How many students like football only? So when you mean only, it means we don't want any football and tennis, football and other sports. We just want football only. So once again, the very tip here is to take it literally. In this case, football only is 32. So that's the answer there. But however, if there's no mention of only, like how many students like tennis, we can actually include. If there's no mention of only, we can actually include the intersection. So these people like tennis, and there's no restriction that it's only tennis, so we can include these people here. So 15 plus 12, that's 27. Next, how many students like football and tennis? So football and tennis, so therefore that's the intersection, just 15. So hopefully this short but hopefully concise definition of what do you call this, Venn diagrams and sets gives you an idea on what to expect for the test. This is a grade 7 topic. We just actually, what do you call this? We just actually rediscovered it, reviewed it. Next, simple probability. Simple probability is defined as doing. Did I even add it? Yes, okay. This is simple probability. Sorry. So, actually, it's worth mentioning that theoretical probability, it's not here, but it's worth mentioning that theoretical probability assumes complete fairness. So, like, let's say a dice, right? A dice has 6 sides, so therefore each side has an equal chance of landing 1/6. However, if you roll, let's say 100 times, right? So that's what I call theoretical probability. But experimental probability is obtained from experiments. So let's say I roll 100 times, and then I list the values into a table. So something like this, and then that's the experimental probability. So what you just need to do is to find, for experimental probability, is to find the favorable outcomes out of the total number of outcomes. So that's the difference between theoretical probability and experimental probability. With that, let's talk about cards. Theoretical probability. If a card is selected randomly, determine the probability of getting a red card. Let's not take that out of context. Red card. So basically what it's talking is the standard deck of cards, where we have the clubs, I think. The clubs. How do I draw it? Like this. And then the spades. The clubs and the spades. And then we got the diamonds and the hearts. So each of these suites contains 13 cards. A total of 52. So we want a red card. So that's 13 plus 13, which is 26 over 52, or equal to 1/2. Next, a queen card. So a queen card, what do I mean by this? So there's actually a lot of different types of cards, and I'll list them down. 2, 3, 4, 5, 6, 7, 8, 9. Hold on. 1, 2, 3, 4. 10, J, Q, and K. So there's 13 different types of cards. So as you could see, you could probably see where this is going. 13, so one of each, one of each, one of each, and so on. So what's the probability of getting a queen? So we have one queen over here, one queen over here, one queen over here, one queen over here. So we have 4 over 52 because one from each suite. 52 for the total cards. Simplify that, and that's 1 over 13. Next, a spade card. So spade card, spade is one of the suites over here. So 13 over 52, and that's equal to 1/4. So that's simple probability there. You're just gonna roll once, and yeah, that's gonna be it. It's just one singular event. Meanwhile, as for compound probability or compound event, think about this. A box contains 4 red balls, 5 yellow balls, 3 green balls. If a ball is picked at random from the box, find the probability that a ball picked is a yellow ball. So as you could see, there's only one favorable outcome here, yellow. But for compound, we have yellow or red. If there's more than one favorable outcome, it's called the compound event. So let's solve for this one. Only the compound one. So we have, okay, yellow ball. Yellow or red ball. So we have 5 yellow balls plus how many red balls? 4. And then that's all over the total. So 4 plus 5 plus 3. 4 plus 5 plus 3. Simplify. This is going to be 9 and this is going to be 12. 9 over 12 is equal to 3/4. So the answer for this one is 3/4. Very simple. It's very simple. You just need a bit of analytics here, and I'm pretty sure you can pass this one. Right. Let's continue. So that's very good. That is simple and compound probability done. Okay. All right, now time for mutually exclusive and non-mutually exclusive events. A box contains 2 red, let's write the given. 2 red, 4 green, 5 blue, and 3 yellow marbles. If a single random marble is chosen from the box, what is the probability that it's a green or red marble? So, we have, let's see, we have 2 reds plus green, 4 greens all over all the outcomes. 2 plus 4 plus 5 blues plus 3 yellows. This is equal to 6 over 14 or equal to 3 over 7. So all right, so okay, so that's the answer over there. Now, I'm gonna show you the difference, but let's see. Next, this is an example of mutually exclusive. So, mutually exclusive. Then this one, the next one is gonna be non-mutually exclusive, and I'll show you why later. Determine drawing the probability of the following event. Drawing a red card or a queen from a standard deck of cards. So we have a red card over here. We answered that already. And because red makes up half the deck, we know that red card is equal to 26 over 52. However, we also want to find how many queen cards are there. So queen cards, we also answered that one. That's 4 over 52. But you might be saying, okay, let's just add it. But no, some of these queen cards are already part of these red cards and vice versa. So what do we need to subtract then? So let's try to look for queen red cards. Queen red cards, so that's these two, right? Queen reds. So the queen diamond and the queen hearts. So that's equal to 2. So therefore, 2 over 52. Now, we do 26 over 52 plus 4 over 52 minus our double counted ones, which is 2 over 52. And that's equal to 28 over 52. Let's simplify that. 28 over 52 is equal to 7 over 13. So, I think you can already see this. Mutually exclusive event, as you could see, the red or green marble, it's mutually exclusive and it cannot happen at the same time. So, if I draw just one random marble, there's no chance that it will just be red and green. After all, the marbles are only one color, so it's not gonna happen. So therefore, this is a mutually exclusive event. Whereas this non-mutually exclusive event, as you could see, I have some cases where I satisfy both requirements here. So the red card and a queen. So as you could see, I satisfied both conditions. So therefore, these two events can happen at the same time. And when graphed on a a Venn diagram, this is actually referring to the intersection, this one. So therefore, you just need to identify if there's an intersection or not to determine if it's mutually exclusive or non-mutually exclusive. Same thing here. Actually. That's basically the same concept and same logic, almost the same logic as dependent and independent events. So, let's solve this. Two cards are drawn from a standard deck of cards in succession. What is the probability of getting an ace and then a queen? So an ace is a type of card here. So ace, we have 4 of it. So that's going to be 4 over 52. Now, the formula for this one is to times it. So times, what's the next probability? And then a queen. So we are going to replace, once we draw the ace, we put back. So there's still 52 cards on the deck. So 52, because we put the ace back. Let's say we put the ace back. And now we need a queen. And then a queen is just as likely as an ace because it's one of the 13 types over here. So therefore, it's 4 over 52 times 4 over 52. So 4, let me type that in my calculator. 4 over 52 times 4 over 52. That's equal to 1 over 169. So I think you can start to understand why there's a with the replacement. But let's try. Okay, 2 cards are drawn from a standard deck of cards in succession without replacement. So same question. So as you could see over here, we have once again 4 over 52 because the ace just stays the same. But the keynote here is without replacement. So because of this without replacement, we don't put the pulled out ace anymore or whatever we pulled out from the first run. We need to remove it, set it aside. So therefore, we have 1 less card than 51. However, since we still have the same amount of queens, we still have 4 of them, we can just continue with that. So by just changing one number, we can put in our calculator that this is equal to 4 over 663. And there you go. That's basically all you need to know for the upcoming written work here. So once again, the dead giveaway. Independent is with replacement and dependent is without replacement. The reason why this is dependent, it's because it's depending on... So this outcome will be affected by whatever goes with this. So your outcomes might be a little bit changed if you, let's say, do not roll a favorable outcome here or roll a favorable outcome here. It's dependent. But here, your chances remain constant. It's because you keep the things you drew and you place them back, giving you an equal chance. So the best version of the dependent one is the lottery. Because as you draw numbers, favorable numbers, so let's say you start matching first number, the number of favorable outcomes decreases. So that's all you need to know for this late night session here. It's 10:54 p.m. Not too late, actually. I recorded later than this. But once again, thank you so much for your patience here. And yes, I did record this all in one breath. Thank you guys for watching. Take care of yourselves, and I'll see you next time. And please wish me luck in the upcoming science quiz. Thank you.